and you can start speaking.
Okay, so 5, 4, 2, 1. Let's start. Okay, good evening. So very welcome to the first virtual thematic workshop. We have the Young Scientists Forum. This forum is based on all the scientists from China and the Latin American and the Caribbean. So thanks for our supporters and also our organizers. Our first topic today, we're talking about the groundwaters from the top scientists in China and also Latin American and the Caribbean. So first, let me introduce the opening remarks speakers. Professor Dr. Ying Li, who is the Director General of the Bureau of International Cooperation, Chinese Academy of Science, and also the Chair of the T1's Young Affiliates Networks, T1s. The next speaker is Professor Dr. Virgilio Augusto Randomita. He is the member of the Brazilian Academy of Science, BAS, and the World Academy of Science, TWAS. Since 2019, he is the head of the TWAS Latin American and the Caribbean Region Partner Office. The next speaker will be the Professor Dr. Yi, who is the Deputy Director, CAS, Institute of Microbiology, Chinese Academy of Science. He is also the chair of the Young Innovation Promotion Association of Chinese Academy of Science. The last speaker will do the opening remarks is Professor Dr. Franco Grebizo, who is a member of the National Scientific and Technical Research Councils, also associate professor at the National University of San Martin. He is also the member of the TWAS Young Affiliates Networks and the Argentina Young Academies. So let's welcome Professor Dr. Ying Li for the opening remarks.
Thank you very much, Professor Fang, for kicking off this workshop, which I think is very important. And thank you very much for inviting me to attend this opening session and give my comments. So first of all, on behalf of the Bureau of International Cooperation of the Chinese Academy of Sciences, so may I congratulate to the opening of this virtual thematic workshop on discussing the groundwater. I think this is a very important step for enhancing and fostering the collaboration among the young scientists between China and the Latin America and the Caribbean region. I'm very pleased to meet virtually with Dr. Virgilia Almeida, who is in charge of the TWAS Lab Prep, which I trust we get a lot of support from the regional office, the regional partner of TWAS under your leadership. And I'm very pleased that you also showed your support from either the Brazilian Academy of Sciences and also from the regional partner sites to the organization of this workshop. I'm also very pleased that IPA, which is led by Dr. Yi Shi, and the Argentina Young Academy of Sciences, which is led by Dr. Franco Cambrizia, which this is a very important step that you achieve the consensus to organize these long-distance virtual workshop despite the pandemic. We are all affected by the pandemic, but our enthusiasm and our passion was not affected. So I believe with the opening and the e-discussion of the important issue, the groundwater and the science technology behind that, we could build up our relationship and our partnership online, and to make a good basis for when we meet in the future. We could even discuss what kind of ideas that we could create jointly, and could we find other resources to support our joint projects, etc. So with this, I would like to also thank the organizers for instance, Professor Fang and Franco and others involved in preparation, and the speakers today invited, which is all vital for the organization and for the holding of this virtual workshop today. So I hope you will all get some new knowledge, new experience by sharing to each other. And I sincerely hope this will be a very good start for the next in the thematic areas that we both choose that are with mutual interest and with mutual importance for both China and Latin America and the Caribbean. And with this as a start, I hope that the EPA and also the Argentina Young Academy and also TN and AJA-TYAN-CAS, which would attract more capable young scientists to join this online discussion on various aspects that we are interested in, and so as we could take this opportunity to increase our impact and to involve or to create more potential collaborations for the future. So last but not least, I also want to share with you, the audience, that Professor Franco and Cambrezzo has also been appointed as one of the members of the AJA-TYAN-CAS, which we heard recently got approval from the AJA Executive Director, Professor Morenzi, which this is a very important step that connecting TN with the regional partner affairs. So I trust with the strong support from Professor Virgilia Almeida, I trust the Caribbean and the Latin American region will play an even greater role in promoting the development of young scientists, not only regionally, but also globally. So with all this, I wish the workshop a great success, and at the Bureau of International Cooperation and the Chinese Academy of Sciences, we will try to do as much as we can to support the future exchange and also the collaboration among the two regions. Thank you very much.
Good morning. Can I go ahead?
Go ahead now.
Okay. Good morning to all friends in Latin America and the Caribbean, and good evening to friends in China. I would like to thank Professor Lee warm words for in these opening remarks. I think that's an important milestone for the collaboration among scientists in Latin America and also with Chinese scientists. On behalf of the Brazilian Academy of Science, I would like to welcome all attendees of the workshop. In particular, I would like to thank the researchers from China and Latin America and the Caribbean that will present results of their research work. I'm delighted to participate of the opening of this workshop organized to reach young scientists of different parts of the world. The Regional Partnership for Latin America and the Caribbean, LACREP, of the Network of Young Affiliates, TIAN, and the TUOS, World Academy of Science, organizes this virtual scientific workshop. And this initiative has a partnership with the Association for the Promotion of Youth Innovation, which also brings together the Association of Youth Intervention Programs and the Chinese Academy of Science. This partnership aims at creating a space for youth to engage on specific topics related to global challenges such as groundwater. Optimal management of global water resources present one of the most crucial challenges of the 21st century. The world population is expected to reach 8.6 billion in 2030 and almost 10 billion in 2050. And the world's population that live in urban areas is expected to increase by 68% by 2050. Most of the world's population growth will occur in developing countries where water is already critically short and many of the residents are impoverished. Even today, more than 2 billion people do not have access to safe and affordable drinking water, and perhaps twice that many lack adequate sanitation services. In fact, inadequate drinking water quality is a leading cause of infant mortality worldwide. So this emphasizes the importance of this workshop. The purpose of the series of events is to promote scientific collaboration between Chinese and Latin American and the Caribbean scientists, keeping the international young scientific community active during this pandemic period. Relevant topics in various areas of knowledge will be covered, such as in future workshops, such as earth science, ecology, mathematics, physics, renewable energy, smart cities, food, biotechnology, agriculture, social science, economics, and urbanism, among others. Finally, I would like to thank the organizers of the workshop, the Chinese Academy of Science, the TIAN, TUOS, all of them that made possible to have this event today. And I would like to wish you all a very productive workshop. Thank you. I'm done. Thank you.
Okay. So hello, everyone. Nice to meet all of you in the first virtual thematic workshop with the scientists from China, Latin America, and the Caribbean region. So this thematic workshop will plan to consist of a series of webinars with different topics regarding global challenge. And today's topic is about groundwater. And we have evolved senior leading scientists and junior young scientists in this field. And on behalf of EPA, I welcome all the people involved in this webinar and wish this webinar will make a great success. And then I will share my screening to briefly introduce the EPA. Okay, so EPA was founded in 2011 by Bai Chunli, the president of Chinese Academy of Science, aiming to provide supports for excellent young scientists in promoting their vision and interdisciplinary capacity. And now it currently has about 4,500 members, and about 8,300 of them have received national talent funds, including the Distinguished Young Scientist Program or the Outstanding Young Scientist Program from the NSFC. And EPA membership is a credential in career advancement and performance reviews. Now, EPA has its own structure of General Assembly, and EPA members are from 109 CAS institutes across the country and organized into 6 disciplinary branches, including physical science, chemical material science, life science, geoscience, engineering and equipment, and also information management, as well as 13 regional local branches. And in addition, EPA covers 8 innovation fields in basic interdisciplinary science, advanced material, energy, life science, health, ocean, resource, and ecology, information, and also space. And each CAS institute will have an institutional EPA group to keep members stay connected and play a leading role in the young scientist-related initiatives. And our EPA members has evolved a lot of big scientific achievements, such as the FAST, NI for the universe, and also the DAMPER, which is hunting for the dark matter in the space. And also some young scientists is involved in leading the era of quantum communications, and also the space lab. And also the East, the artificial sun, and also the hydro equipment to explore the deep sea. And also the Beidou satellite, which is very important for the global network of navigation satellite system. And also better ways to better agriculture. And for the energy field, we also have technology to save oil with coal. So all of these big achievements is made by the scientists and also the young scientists from the CAS. And also the EPA members has launched a new multidisciplinary journal, the Innovation, in May 2020 this year. And the editorial board member, including 1 Nobel laureate and also 21 academicians from different countries and 45 international scholars.
Hi, Shi. Can you hear me? So Franco, maybe you can introduce from your part. Yes.
Yeah, sure. Let's do that.
It's, I just lost.
Yes. Are you here? Yishi,
yeah, I'm here.
Yeah.
I just come back.
Go ahead. Yeah.
Yeah.
Please.
Yeah. So I can't remember where which slides I just disconnected.
You were talking about the journal. This is a very good example of.
Okay. Sorry. Just I will share. Okay, so EPA members has launched a new multidisciplinary journal, so the Innovation in May 2020. And now the journal has a editorial board member, which includes one Nobel laureate, 21 academicians from different countries, and also 45 international scholars. So finally, IPA hope to establish cooperations with the young scientists from all the world. And we hope to connect all the young scientists on the way to see the unseen and change the unchanged. Thank you very much. Yeah. Okay.
Thank you, Xi, for your presentation. Let me share my screen. I think you can see it. Okay. I would like to start expressing my gratitude to all the other, the partners, organizing and supporting institutions for making this event possible. Thank you, Professor Lee, for your kind words and also for building this bridge between TYAN and YIPA. Your role as Director General of the Bureau of International Cooperation at the Chinese Academy of Sciences and as the chair of TYAN was key to make the dialogue between these two organizations possible. So thank you. Thank you, Professor Almeida, for your words. And also for your support, not only for this particular event. Professor Lee also mentioned something, but to us, LAGREP, and as well as the Brazilian Academy of Sciences, have been very supportive of TYAN since the very early days of this network. This is showing a deep commitment with not only with TYAN, but also with the young scientist community in general. So, and as I would like to take this opportunity to communicate and also to thank LAGREP because of this new agreement, or TUAS LAGREP and TYAN have just made a new step towards strengthening this cooperation, this particular collaboration. These two organizations have just agreed to formally appoint a TYAN representative as part of this TYAN LAGREP executive meeting, and we firmly believe that this partnership and appointment will bring more opportunities and will have a positive impact on the young scientists in the region. So thanks again, Professor Almeida. And thanks, Xi, for your very detailed and impressive introduction about IPA. I would like just to share with you, let me see, a few words about the two other organizing institutions that I am represented today. One of them is TUAS, Young Affiliate Network. You hear about this today, but TUAS, TYAN is operating under the umbrella of the World Academy of Sciences. Was launched in November of 2016. It's growing very fast. Today, TYAN embraces about 150 active young affiliates and alumni, covering many different countries and field of knowledge. TYAN envisions a world connected by scientific cooperations, and it is intended to catalyze interdisciplinary research and development collaboration among all the TYAN affiliates and alumni members to address different challenges with particular attention to those affecting the developing world. To this end, TYAN has organized many activities, including this kind of interdisciplinary thematic workshop. TYAN is also aimed at work with partners to build collaborative networks. And in this matter, TYAN has been very supportive with the establishment of the Argentinian Young Academy. This is the other partner today that I want to introduce you. The Argentinian Young Academy is its very early stage of its life. It was launched last April 2020. AJA envisions a society guided by facts and policies based on scientific evidence, and it embodies principles of co-participation, quality, equity, autonomy, and self-determination, transparency, interdisciplinary, multicultural, and pluralist exchanges, with the particular with particular emphasis on issues with high societal relevance. To this end, AJA will work to establish a platform aimed at empowering young scientists to grow independence and to be involved in public policies. And in this regard, this young academy will work to connect academic sector with the decision-making bodies to establish a more effective channel for communication. Without further ado, I would just, on behalf of the organizer, I declare this first workshop, virtual thematic workshop, open. I want to thank the speakers and moderators for their willingness and enthusiasm to be part of the first edition of this series of webinars, virtual workshop, sorry. And as moderator today, two outstanding young scientists were chosen from the Latin America and the Caribbean region. The moderator will be Dr. Emilio Martínez. Dr. Martínez has a degree in geology and also master and PhD degrees in geosciences at the University of Sao Paulo, Brazil. In 2009, she was appointed as professor at the USP. She has experience in the field of geosciences with emphasis in isotopic geology, working mainly in groundwater. She also has experience working in the field of natural disaster prevention with focus on risk perception and education. She's part of the Geochronological Research Center, Groundwater Research Center, and also Center for Disaster Studies and Research, all of them at the University of Sao Paulo, and is also a member of the National Forensic Isotope Network. And from China, the moderator will be Dr. Xiao Fang. Dr. Fang received his PhD degree from Hokkaido University, Japan. As part of his previous research experience, Dr. Fang has been involved in research projects in the framework of different international institutions, including the core research for evolutionary science and technology at the Japan Science and Technology Agencies, and the Helmholtz Association Young Scientist Program in Germany. In 2015, Dr. Fang joined the Key Laboratory of Optical Physics as Associate Professor at the Institute of Physics, and his main research interests include novel subcycle waveform synthesis for attosecond science and compact X-ray sources. So, Veridiana, thank you very much, and we are ready to start. Veridiana, it's your turn, please.
Thanks, Franco. So should I? Okay. So should I share my screen, because I will introduce the Professor Lu, and also the
Okay, can I say some words before?
Yeah, please go ahead.
Okay, so I'd like to thank the kind introduction of mine, and I just want to welcome everybody and say that questions can be sent by the chat, and we will provide the organization of that and to report the speakers. Okay, I think that's it. Is there anything else, Shabu?
Yes, so unfortunately, our Zoom platform is only allowed 300 audience to join our meetings. So we also share this meeting online from the YouTube outside, and also from the Bilibili, from the IOP platforms. So I think everybody can see this wonderful presentation and these wonderful young scientist forums. So for save the time, let me introduce our next speakers. I would like to share my screen. Here we are. Okay. Duplicate it. So yes, please let me know if you can see it off screen from your side.
It looks good. Go ahead.
Okay. So our first speaker is from the University of Science and Technology of China, Professor Zheng-Tian Lu. Professor Zheng-Tian Lu is the professor at the Department of Modern Physics, and also he is the Dean of the School of the Gifted Young and at the University of Science and the Technology of China. He received his bachelor degree from the USTC in 1987 and also a PhD from UC Berkeley in 1994. Before he came back to China, he was a senior scientist at Argonne National Laboratory and also a professor at the University of Chicago. Throughout his career, Professor Lu has been developing techniques of laser manipulation and laser spectroscopy of atoms and applying this technique to ultra-sensitive trace analysis, studying nuclear structure, and testing fundamental symmetries. He received tons of the awards, including a U.S. Presidential Early Career Award in 2000. Also was elected a Fellow of the American Physical Society in 2006. He received the Society Francis Pipkin Award in 2009. He served as a member of the U.S. Nuclear Science Advisory Committee in 2011 to 2013, and also as the chair of the topic groups of precision measurement and the fundamental constants of the American Physical Society in 2015 to 2016. He currently serves on the board of the Max Planck Institute for Nuclear Physics, Germany, and the National Institute of Metrology, China, and the National Laboratory of Physical Science at Microscale, China. Thank you very much, Professor Lu. So very welcome, and please, this is your stage.
Okay. Hello, can you all hear me?
Yep.
Yes, super.
Okay, hello everybody. It's a great pleasure and an honor to be speaking here. I want to thank the organizers for inviting me, giving me this opportunity. And I want to thank you all for attending this discussion. I'm speaking from the city called Hefei, H-E-F-E-I. It's about 500 kilometers west of Shanghai. And this is one of the hottest weeks in this summer. Today it's over 36 degrees Celsius. And I'm actually very pleased to hear earlier that my friend, Professor Emilio Martínez from Argentina told me that it's below zero over there. So it brought me a sense of coolness already. It's a great pleasure. And today I will be speaking on atom trap, Krypton 81, and its use for global groundwater study. These are my colleagues at the USTC. We are laser laboratory for trace analysis and precision measurement. Our website is AJA-TYAN-CAS. ustc.edu.cn, and there will be a lot of information. If you're interested, please go visit our website. We are generously supported by the National Science Foundation of China, by the Ministry of Science and Technology, and by the Chinese Academy of Sciences. So this isotope, krypton-81, it's radioactive, and it's produced by cosmic rays in the upper atmosphere. And once it's produced, because it's a gas, krypton is a noble gas, it stays in the atmosphere for the longest time, as long as before it radioactively decays. So as a result, it's very well mixed in the Earth's atmosphere and achieves a uniform distribution. The isotopic abundance of krypton-81 is a constant. It's the same everywhere, whether it's in Argentina, in China, the US, or Antarctica. In the atmosphere, the krypton-81 has the same isotopic abundance. And we've actually measured all these samples and verified so. Now, when surface water exchange air, krypton with the air, it acquires the same isotopic abundance. We call that I0, okay? Once the water is separated from the air, say as the water goes underground, or if the water freezes into ice, then there is the exchange stops, and there's no more fresh krypton-81 comes into the sample. So from that moment on, the isotopic abundance of krypton-81 decreases according to the radioactive decay law by a factor of 2 every half-life of krypton-81, which is about 250,000 years. Okay, so as the water flows along underground, the isotopic abundance of krypton-81 decreases over time. And so that's how we use to date the water body. Water itself is just a molecule, it does not have age. But when we say the age of groundwater, we mean how long ago this water has been separated from the air. This is a very useful information because this underground flow line, you cannot really see. The flow is very slow. It can be as slow as 1 meter per year, so it cannot be directly measured. But if you go to these well sites and you sample this water and determine its age, then you can plot out this flow line. And that's useful information for groundwater management. So as you listen to this principle of radiokrypton dating, it probably reminds you about radiocarbon dating. In fact, radiocarbon dating is based on a very similar principle. Carbon-14 is produced by cosmic rays, and once it's produced, it oxidizes into a CO2 gas. And as a result, it stays in the air for a very long time and gets mixed well in the atmosphere. And once it goes into the water, it radioactively decays according to this line. So by measuring its relative abundance, you can determine the age of water or other specimens. Now, when you look at this decay line, if the age is much shorter than the half-life of carbon-14, this part is kind of flat. So carbon-14 dating is not sensitive. When you go way beyond the half-life, this part is quite steep and the sensitivity is really high. However, there's something else that comes in that causes difficulties. When you sample water or when you analyze isotopes, there's always a little bit of mixture of air going into the sample. Okay, so it's a modern contamination. Suppose a modern contamination is at 1%, then when you measure carbon-14, you will always get 1%. no matter how old the sample is. So if you use that 1% to calculate the age, you always get about 30,000 or 40,000 year age for the groundwater. And if you look at the data all across the world, you see a lot of groundwater ages are pinged at 30,000 and 40,000 years. And the reason is because of this. It's a sampling contamination problem. Nowadays, when we go to the same site and apply Krypton 81 analysis, we found the age is not just 30,000. It could be as old as 300,000 years old or even older. So for this radioactive isotope of carbon-14, there is an effective age range. It goes from a few hundred years to about tens of thousands of years. And within this range, carbon-14 dating works well. Beyond that, you need to find other radioactive isotopes. So in the atmosphere, there are 3 other long-lived radioactive gas isotopes. It's Krypton 81, argon 39, and Krypton 85, argon 39, and Krypton 81. Each isotope has a different half-life, and it just so happens that they fall in different orders of magnitude. So their effective age ranges link together to cover continuously from a few years all the way to about 1.3 million years. Now, the analysis of carbon-14 have long been solved. I think it has been solved since the 70s. These 3 krypton and argon isotopes had been difficult to measure before, but now with the atom trap technique that we developed, we have also solved the analysis problem of these 3 isotopes. They're really ideal for dating environmental samples because they're inert, chemically inert, so their transport process in the environment is quite simple to understand. And they're also gas. Why is gas so important? Well, so one common isotope that had been used before was chlorine 36. It has a long half-life, 300,000 years, about the same as Krypton 81. So people have been using that. But chlorine is not a gas. So if you look at this initial distribution over the continent of the United States, you find that some places the initial distribution is like 50, other places it can go up to 1,000. So initial value can vary a lot. That makes the determination of the age difficult and unreliable. With krypton gas, the initial distribution, as I mentioned, is uniform all across the continent or even across the whole globe. So that makes gas dating so much more reliable. So here it is. This is the mission of our laboratory. We want to provide key timing information for the study of global and regional water cycles. Water goes around the world. Ocean currents flows around the world on a time scale from 10 years to a few thousand years. Glacier ice can go from years to hundreds of thousands of years, maybe even 1 million years. Groundwater goes also, the shallow groundwater goes for a few years. Deep groundwater, we know, can go above 1 million years. To study all these cycle processes, knowing the time is very important. We need isotope dating. So these isotopes were known since the 1960s. Professor Hans Oeschger at the University of Bern in Switzerland and his then student, Ugo Loosli, they already discovered these isotopes in the atmosphere. And they knew this would make ideal dating tracer isotopes. But at the time, they couldn't know how to detect them in the reasonable environmental samples. The difficulty lies in the extremely low isotopic abundances. Krypton-81 has an isotopic abundance of 6 times 10 to the minus 13. Argon-39, 10 to the minus 16. So this is way below what the gas mass spectrometer can analyze. The usual mass spectrometer can analyze maybe 10 to the minus 6. And if you work hard, maybe you can get to 10 to the minus 8. But these are at 10 to the minus 13, 10 to the minus 16. And that's why it's so hard. In a given liter of water, you can expect to find about 1,000 Krypton-81 atoms. So really, we need to count individual atoms in the water sample. So this is a technique we developed to count Krypton-81. We give it a name. It's called atom trap trace analysis, or AJA in short. Okay, you have krypton gas going into this tube, into a vacuum system, and as the atoms race along in the vacuum tube, we have laser light come in from the side to collimate the atomic beam. We have this laser beam that goes against the atomic beam, shining onto the atoms head on to slow the atoms down. And by the time the atoms get to this point, it's almost stopping. And we use 6 laser beams to capture the atom. An atom in the trap is actually bright, looks like a bright dot, and we can image that dot with a CCD camera. So we can see a single atom, as you see very clearly. Okay, so this is how we count individual atoms. All these techniques of laser trapping, laser cooling were developed in atomic physics since the 80s. Several Nobel Prizes were given to physicists who developed atom trapping and cooling. For example, this is Professor Stephen Chu, who received the 1997 Nobel Prize in Physics. You may have heard of him because later on, he was the Secretary of Energy for the Obama administration. And recently, actually Steve Chu's mentor, Arthur Ashkin, received the 2018 Nobel Physics Prizes at the age of 95. So they were the pioneers of laser application on atoms. The principle of slowing down atoms is actually quite straightforward. The famous physicist Albert Einstein pointed out that photons carries momentum. When a laser beam shines onto your hand, you may feel the heat of the laser beam. But there's also a force from the laser beam. This force is very small because the photon momentum is tiny, okay, and your hand is massive. But since the atom itself is pretty small, even the tiny momentum kick from the photons matter. Okay, so you can think of the atom as a large basketball, and you can think of the laser beam as a stream of ping pong balls. And if you shoot lots of ping pong balls onto a basketball, you can actually accelerate the basketball. So that's how we do it, okay? So for Krypton-81 atom, a single photon kick can change the velocity of the atom by 6 millimeters per second. But the transition rate is very large. The photon scattering rate can go at 10 million times per second. So you multiply these two, you get a very decent deceleration force on the atom. Okay, that's how we slow the atoms down. That's how we capture atoms. The apparatus is about 2 meters long. This is a picture of the apparatus in our laboratory at the University of Science and Technology in Hefei. Samples, so for example, samples from all over the world gets connected here. The krypton gas leaks into the chamber and they race down this pipe, and this is where we capture the atom, and this is a CCD camera that can see the image of a single atom. And so this is atomic beam apparatus. Laser beams are prepared behind these walls on the laser table. So let's open up these walls to show you what the laser beams are, how the laser beams are prepared. So this is a laser table. So all these about 7 or 8 laser beams are prepared on this table, and they're patched over by optical fibers onto this vacuum system. Okay, so these are our apparatus. And this is a signal. So when you see a bright dot, how do we know it's a krypton atom? How do we know it's a krypton 81 atom and not a different isotope? Well, each atom has its own characteristic frequency, okay? And they're different for different species of atoms. If you recall, neon atoms appear red, okay? Sodium atoms appear orange, okay? So their frequencies are very different. Even for the same element, different isotopes, the resonant frequencies are slightly different. Between krypton 83, krypton 81, the frequency is off by about 100 megahertz. These are what we call isotope shifts because their nuclear masses are different, nuclear volumes are different, so their atoms are slightly different. Modern technology allows us to place the laser frequency precisely onto the resonance of krypton 83. Then we can trap krypton 83. We can tune the frequency over. It's all controlled by computers, and we can trap krypton 81. So by doing so, we can clearly see this krypton 81 peak and krypton 85 peak. Okay, so that's how we tell which isotope we are looking at. Now, these 3 isotopes are present in the same sample, but I didn't plot them onto the same plot. I separate them because the central peak is of krypton 83. It's a 10% abundant isotope. Krypton 81, 10 to the minus 13. So the 2 peaks are different in height by 11 orders magnitude, okay? And regular laser spectroscopy techniques will not be able to separate these 3 peaks because this wings of this gigantic peak, 11 orders of magnitude higher, will completely bury these 2 small peaks on the side. However, our atom trap technique can clearly separate the 2 peaks out of this background. That's the magic of the AJA technique, okay? And it's very, very clean. If you look at this peak, okay, and it shows that if you tune the laser frequency away from krypton 81 resonance, the background is not just low, the background is 0. There's 0 chance for this neighboring isotopes, 11 orders magnitude more abundant, to leak into our detection system. And this is a unique property among all trace analysis techniques, but it's a contamination-free detection. So we can see these rare isotopes and we can analyze its abundance simply by counting them. The more abundant isotope will appear more frequently into our trap. And we always measure ratios between the radioactive krypton 81 and an abundant, say, krypton 83 isotope. By taking the ratios, we can get rid of most of the drifts and fluctuations in our apparatus. As you see in this figure, that we can deliberately make our instrument to drift so that the counting rate for the isotope can go up and down by a factor of 10 within the same sample. Usually we don't do this, but just to test the robustness of our apparatus, we deliberately make them change a lot. However, you can see the ratio does not change. It falls onto the same line. So that passes our self-consistence check. We also compare our results with our friend Roland Perchert at University of Bern, who can actually simulate samples of different ages because he has a sample with 0 krypton 85. he also has a sample from air with krypton 85. He can mix these two mother samples to produce a series of calibration samples and use that to test our apparatus. In fact, every collaborator, every user, for example, my friend, Professor Emilio Martínez, he can actually test us. You don't need an AJA system at home just to test whether we can make correct measurement. I'll tell you how to do this. So you sample, so you collect 10 different samples, okay? And the number 3 sample, you don't send us all of it. You send us half of it, you save half for your own. And you don't need to tell us which sample you saved, okay? And so we analyze and we provide the results. Now, a year later, you can send us 10 new samples. And among the 10 new samples, you mix that, you place one of this old number 3 samples within the new group of 10. And you don't need to tell us which one it's a repeat sample, okay? And you see whether we give you the repeat results. So that's a simple way for a collaborator, a user of our facility to test whether we give the correct results. And we encourage our collaborators to do so. So that was Krypton 81 and Krypton 85. Those we solved a few years ago. More recently, we have built up a system to analyze argon 39. And this is very, very difficult because its isotopic abundance is only 10 to the minus 16. And we are able now to count argon 39 at 10 counts per hour. And it's a world record. At 10 to the minus 16, we can count the atoms at 10 counts per hour. So this is these are 3 apparatus that we have working in operational mode in our laboratory today. Each of them is tuned to analyze one specific isotope, krypton 81, krypton 85, argon 39. And we are actually building up more capacity because there are more demands from around the world. So by next year, we hope to double the capacity, to add 3 more atom traps and double the annual analysis capability. So that's our goal. And let me tell you the whole radiokrypton dating procedure. First, you need to extract the gas from water. Now you can also just collect the water and send it to us, but that's kind of cumbersome to ship water over a long distance. So what we usually do is we take a gas extractor. It's based on a hydrophobic membrane device, and you can carry it into the field by the well side. So that you can collect the gas from the water, and you can return the water back into the field. Once the gas arrives in Hefei, we actually run through a purification process to use chemical and physical method to extract krypton and argon from the bulk gas. And this is a picture of our apparatus. It's all computer controlled now. And so we can recover the krypton and argon with over 99% efficiency and with very high purity. So this is done with this machine. And that's our graduate student who developed this analysis apparatus, Dong Xizhe. Okay, so here's a procedure again. From the well side, you extract the gas, and we need about 1 liter of gas. You send this bottle to us. We run through the purification setup to get krypton out of the gas. Krypton is about 1 ppm in the gas. So from 1 liter of air, we get about 1 microliter of krypton. And then we leak that into the atom trap device, and we count the atoms. From the counting of the atoms, you can use this simple formula to get the age of the water. And so this is our precision plot for, this is what we currently can do. And so how precise can we determine the age? Well, it depends on what the age is, and also depending on how much samples you send us. Certainly, the more samples we have, the more precise we can produce results. And also has to do with sample ages. If the sample age is too short or too long, then the precision drops. As I told you before, there is the effective age range for each working isotope. So far, we've been collaborating with hydrologists, glaciologists, and oceanographers from around the world. And in particular, for South America, we have collaborated with scientists from Brazil. We are now collaborating with scientists from Argentina, and also previously with scientists at Chile. So if you're interested, I would love to collaborate with more scientists in Latin America. If you're interested, please visit our website over here. You can Google AJA Primer to find us, or if you use your cell phone, you can scan the QR code. You get to our website. On the website, we will explain how we do the analysis, what are the requirements. We also present the list of all the related publications. And we also tell you which groups around the world who are capable of field sampling of groundwater. The first time when you do it, you need an expert to help you. So go to this website, you find expert groups near you to help you, okay? Once you've done once or twice, then you become an expert yourself, then we will list you as an expert on this website. And once you have a sample, you can send it to us or to one of our fellow groups around the world. So let me just quickly go through a few examples of what we have done. There are so many now, but let me choose a few examples. This is a study of the Guarani aquifer in Brazil and Argentina. Okay, this was a project led by IAEA, where we analyzed krypton-81. We also analyzed total content of helium-4. From that, we can actually determine the amount of helium gas that's being carried by the groundwater onto the surface. And we found that the groundwater is a major pathway for helium to migrate from underground to the atmosphere. So that's one of the studies we did. And this is my colleague, Dr. Zheng-Tian Pang of the Chinese Academy of Sciences. And based on the krypton-81 ages, he produced a groundwater flow model for the Guanzhong Basin in China. This is a region where the groundwater is a valuable resource. So you will know how you will need to know how your groundwater flows on the ground so you can manage the groundwater resources more scientifically. And that's Dr. Pang's work. And here you can actually also use this age dating to determine seawater intrusion rates. This is a work led by Dr. Yossi Yakieli, the director of Israel Geological Survey. And so this was just published in 2019 using krypton-81 dating. We determined the rate of average seawater intrusion from the Mediterranean into the Israeli aquifer. And this is also recent work done in Israel, where by measuring krypton-81 and also the other stable isotope, like the D-axis, we figured that the Israeli groundwater comes from two separate sources. One was charged 360,000 years ago from the Atlantic Ocean. The other is a more recent one from the Mediterranean Ocean. And this work was recently published in the Proceedings of National Academy of Sciences. And for this paper, we actually made the cover of PNAS. I'm very, very proud of this because it's a picture I took and it's not taken by a professional. I was quite taken by this beautiful scenery in Israel. So I just used a normal camera to take it. And I'm very glad that actually made the cover. And also this word that we invented, radiocrypton, made the cover of this magazine also. So a lot of places having find the age very old is not a good idea, because it's not a good news, because old water is difficult to come by. Once you use it, it's gone. It's fossil water. But in this place, we actually hope to find old water. This is a place in Beishan, Gansu, where China is investigating the site, hoping to develop a nuclear waste repository place. So here, you actually worry about groundwater that could gradually carry the contaminants far away. So having the groundwater to be very old is important. It means it's well separated from the surrounding environment. So we are doing this we're in collaboration with China National Nuclear Corps. And in fact, on this area of study, we are collaborating with both the United States, China, and also with Japan. This is a international project pulled together by IAEA to use Krypton-81 as a mean to date very old groundwater. And it's on this project I met my friend and colleague, Professor Emilio Martínez, and we started a collaboration with Argentinian scientists. We are also collaborating with scientists around the world. So that's on groundwater, and on ocean circulation, you can also use the argon-39 to determine the age of ocean water, and from that, figure out the ocean circulation patterns. This is very important. I quote a sentence from Dr. Wally Brooker, who passed away last year. He is a great scientist. He coined the phrase global warming, and also coined the phrase the conveyor belt. This conveyor belt that I showed you earlier, actually that was proposed by Dr. Wally Brooker. And he called for a more dense survey of argon-39 with higher accuracy measurements. He said that would prove of great value in constraining ocean general circulation models. So this is what we're gearing up to do in collaboration with Columbia University. Okay, so that's a very quick rundown of our technique and its usefulness for groundwater study, for ocean currents, and for glaciology, and also for nuclear safety. Thank you very much.
Thank you very much. Thanks, Professor Liu. This is a very wonderful talk, and congratulations for the peanuts. And there's several, actually there are lots of the questions from the Bilibili online broadcasting. Many of them actually is not the scientists. They are some of them. Yeah, some of them is probably from just a high school or junior high school, but I think all the people is very interesting for your talk. There's one question from the audience, is that you said you can test this the sample water and ask your cooperators send them next year. Is that because, and you just test them and they don't have to tell you which one is the repeated one, right? Is that because you can do this very precisely measurement by year? Is it correct?
Okay, so it's a way that we ask our collaborators to test us and also keep us on the edge, right? So we have to do things right. And so if somebody has an independent atom trap apparatus, then we can compare results, right? And but since right now there are very few atom trap apparatus around the world, so this is how you test us. You can basically send a sample, half of the sample this year, and the other half of the sample next year. If we do it right, we should be reporting the same value for both times, right? So that's basically what I was saying.
Yeah, that's good. Otherwise, we could wait for 100 years or 1,000 years to test that. And another question also comes from audience. Is there any fluctuation for your measurement if the underground water was contaminated by some case? For example, if contaminated by some chemical or some radiation or any other, just we unsee some different situation. How do you compare, or how do you separate which one is the measurement error, which one is the real contaminated?
Yeah, so this is another advantage of doing radiocrypton dating. Okay, so there are very little sources of noble gas underground. Okay, and if the water sample is contaminated by, say, other chemicals, they will not change the noble gas part, especially not the isotope part of the krypton. Okay, so if water is simply dirty, that's not a problem. But let me tell you the complications of the krypton dating. For example, during sampling or underground, if there's a contamination of modern air, that will certainly change the results. Okay, and also in many cases, as our hydrology experts will know, that in many cases, water doesn't come from a single flow line. It can actually be a mixture of multiple flow lines, multiple sources. So in those cases, the Krypton 81 analysis will not be able to tell those apart. We can only tell you the average age, the averaged Krypton 81 isotopic abundance. So, when you study an aquifer, you have to measure results over a grid, and hopefully from the grid results, you can figure out the various flow lines. So that's what hydrologists actually do. But if it's just dirty, it's no problem.
Thanks for the explanations. Another question also came from audience. What kind of the laser do you use? Is the standard CW laser, or is the very high-tech laser, or what kind of the power do you need for this laser?
These lasers are now quite common. The wavelength is 811 nanometers, so it's near infrared. And CW, we typically use a few watts of light, so it's not very high power. And it's called a semiconductor laser or diode lasers. And these can be readily purchased from commercial companies.
Thanks, Professor Lu. So is there any questions from your side? Ferdinand?
No, just some people thanking the Professor Lu, and if you want, I can say the names. It's like Pablo Bolanos, congratulations for the PNAS paper on krypton dating. Didier Gasmans say, great talk, Professor Lu, thanks. Thank you, Professor Lu, for your wonderful and inspiring talk in Lee. And congratulations on the great advances from Sibeli Zaki. That's all. Okay.
Thanks. Many thanks for Professor Lu. So for saving the time, should we next move to our next speaker?
Yeah.
Okay, so I have to share my screen. Okay, so I will introduce the next speaker is Daniel Martínez. He is a PhD in geology from the National University of Córdoba, Argentina. His areas of expertise are hydrogeochemistry and isotope hydrology, with a more recent focus on dating water. He is principal researcher of the National Council for Scientific and Technological Research, CONICET, and professor at the National University of Mar del Plata. He has participated in numerous expert missions for the International Atomic Energy Agency, IAEA, has been coordinator of the Commission of Admission to the Career of the Scientific Researcher in Sciences of the Earth of CONICET, and coordinator of the area of Earth and Hydro-Atmospheric Sciences of the National Fund for Science and Technology. His research have been published in more than 70 articles in international journals of impact of his specialty and numerous communication in scientific meetings. He has directed research projects funded by CONICET and the National Agency for Scientific and Technological Promotion of Argentina, the European Union, and the International Atomic Energy Agency. He's currently director of the Argentine part of a bilateral project CONICET, National Science Foundation of China. He is going to speak about Krypton-81 data and its significance in hydrology for a South American perspective. Thank you, Professor Daniel, for this talk. And please go ahead.
Okay. Thank you very much, Veridiana. And do you listen me correctly?
Yes.
Yes,
okay.
Everything's okay. Okay. Then I'm going to share my screen. I acknowledge to the organizer for this invitation. It's a really honor for me to be sharing this workshop with the Professor Lu and the other colleagues, and it's a very, very nice chance to share our experiences and to try to put my perspective. It's the title said from a South American perspective, but of course this is my perspective, that only the perspective that someone who lives in South America. And I think that everyone is thanks to Professor Lu because of his very, very interesting and clear and nice presentation. And as hydrogeologist, I'm very grateful to Professor Lu and all the scientists that perform these fantastic approaches to provide us for a very, very, very interesting and important tool like Krypton-81 and noble gas radionuclides for studying groundwater. I'm from as Mariana said, we belong from two institutes in the Mar del Plata city that are supported by the CONICET and the National University of Mar del Plata. This is a picture of the beach in my city. What happened? Okay. We're talking about groundwater. Groundwater is it's the subject, the leitmotif of the workshop, and groundwater is a component of the hydrologic cycle. Then, if it is part of a cycle, it means that groundwater is moving, and if groundwater is moving, groundwater can be related in a cycle. The time is involved, and it can be related with an age. This is a quite interesting global hydrological cycle balance that was published in 2006 in Science Journal. And I only try to highlight that the total terrestrial precipitation is this amount in thousand cubic kilometers per year. And about more than 25%, more than a quarter of this is moving at subsurface runoff. It means that groundwater is very important in the hydrologic cycle, and a large part of the hydrologic cycle is moving as groundwater. And as it is moving, you can find in the internet and in papers many or several schematics AJA's distribution like this for groundwater. And in these figures, you can observe at the bottom, usually, let's say, millennia, water of several thousands of years old. And it is quite clear that it can be related with depth, because as more distance from the atmosphere, from the infiltration of precipitation, it's supposed that you need more time to put the water there. And the importance of using groundwater AJAs for several studies maybe is quite clear for young groundwaters. This is also taken from another paper. It's an example that in this case, the water which is discharging in this stream is not the result of the present situation, the present land use. If not, you are observing that the water which is discharging in the stream was produced 30 years before of the present moment. This is very important concept for water management or for environmental management. That's you are observing now in groundwater in many cases what has happened many or several years before, and especially we need some tools to determine these processes. The situation for water in Latin America, or especially in South America, from my point of view, can be observed using several statistics. As an example, from these statistics from the United Nations, the freshwater availability in South America per cubic meter per person per year seems to be not so bad. The continent has, you can say, a lot of water, but if we put attention into the situation with the improved drinking water sources, the situation is different, and not all the countries are in a good situation, and in many of the countries, more than 50% of the population is not receiving improved drinking water resources. And of course, if we take a more detailed view and it's happening with statistics, this statistics is not so clear or not so indicative of the real situation. This is the distribution of major climates and regions of South America, and I'm going to comment about my country. In my country, most of the area, maybe more than 50% of the country is below arid and semi-arid conditions. This statistic is showing that most of the people has access to fresh water in the country, because most of the people is living where fresh water is accessible. And most of the people is living in this region, in Argentina. And it implies for the country several problems and difficulties. You have not a good distribution of population because the water distribution is not very good, it's not accessible in all the country. The same happens in other areas of South America. Brazil has very dry areas in some parts, and it has an impact in the economy and the population distribution. Then we have to put attention in groundwater, because groundwater occupies many bases along the continent, and then groundwater is quite well distributed and is an interesting resource to be used. Also, as an example, in this part in southern Patagonia, which is an arid climate, we have aquifers that carry the fresh water and the water available in this region. The study of the ages of this water, this formation, for example, is an interesting point to the management of groundwater in South America. There are most of this water, as you have seen, is contained in big sedimentary basin, and you can expect that it is all groundwater. And there are several studies, same studies in South America previously, and there was based on carbon-14, the previous known techniques. And the first one probably was developed by Professor Tamers. Professor Tamers was working in the Academy of Research of Venezuela. And the first studies from carbon-14 in South America were developed by Professor Tamers. more recently, or just two years before, close to there, Pedro Villegas and other colleagues studied the aquifer of the Urabá Gulf, containing carbon-14 ages up to close to 30,000 years old. In my country, in Argentina, the first studies were developed by Professor Guillermo Bonorino at the south of the province of Buenos Aires in Bahía Blanca, and he measured ages from 10 to 30,000 years old, but he said clearly that to the south, there was water older than the applicability of carbon-14 method. Other measurements of carbon-14 were done on this Patagonian aquifer, obtaining ages about 12,000 years old, and more recently, the group of studies of the University of Rio Cuarto in central Argentina studied the confined aquifers in central province of Córdoba, and they date water from few thousand of years old up to 47. But if you observe the percentage of mother carbon of the samples is 0.28, and in many cases, as Professor Lu mentioned in his presentation, it's indicative that maybe water is much older, because few portion of mother air contamination in the sample can modify the results. The same happened in Brazil. Many studies have been developed. I only collected two in the area of Recife and the Amazon aquifer very recently, and specifically in the area of Sao Paulo. There is in developing a study on Tábara aquifer that has been recently published by Zibel Saki and others, and they also mentioned that the water is, in some cases, older than the applicability of carbon-14 method. And for the end, is mention of the study of the Guarani aquifer, because as Professor Lu already said, the first dating with Krypton 81 in South America, at least until I know, has been done there in the Guarani aquifer in the area of Brazil, obtaining ages of very old groundwaters. The Guarani aquifer is quite emblematic aquifer in South America, because it's a transboundary aquifer occupying 4 countries, and it's outcropping in some areas of Brazil or close to the surface in areas of Brazil or Paraguay, but a very deep position in Argentina and other areas of Brazil, and the water is very old, and that's why it has been studied by Krypton 81 as support for this study that explains the gassing of helium-4 to the in Argentina, in my region, when I live, we have it's the province of Buenos Aires. This is more or less the area of the province of Buenos Aires is 38 south degrees of latitude in the Atlantic coast. My city is here, more or less. And the province is formed by some positive elements. The Martin Garcia Horst is an outcrop of the Brazilian Gill rocks. And then there are 2 low altitude mountain ranges, which are called Tandil and Ventania, and which are separated in 3 sedimentary basins. The Clarimeco Basin is a basin formed during the Paleozoic, and the Salado Basin and Colorado Basin in the south were formed during the rifting of the Atlantic. These 2 basins were formed simultaneously in the late Jurassic and early Cretaceous times, and then they having the similar sedimentary development, including very thick sequences of sediments of about 7,000 of meters, and also the Clarimeco Basin, after despite it is from the Paleozoic, the basin from the Cretaceous and until date has the similar evolution that the Salado and Clarimeco and Colorado Basin, and then the sedimentary sequence is quite similar. We have the three basins, a sequence of Pleistocene sediments at the surface, which is containing an unconfined or semi-confined aquifer, which is below of it. It's possible to find, or it's possible, always it is found. You can observe this sequence of Miocene or Pliocene, upper Miocene and Pliocene marine sediments from marine intrusion. They're mostly clay, and it acts on aquitard. And below this aquitard, that can reach several hundreds of meters of thickness, maybe 3, 4, several hundreds of meters of thickness. There are again deposits of aquifer sand that form aquifers from Miocene age, mostly from middle to upper Miocene ages. With different names in different parts of the province. Maybe in this area, in the Salado Basin, we see the name of Formation Olivos, but is correlated with the Formation Ambucta in the Colorado Basin. And they have similar situations, and they are promising aquifer for studying very old groundwaters, because they are confined but so thick sequence of marine clays, it's expected that groundwater is very old there. But especially in the Colorado Basin to the south, this basin was studied, as I said, by Professor Guillermo Bonorino, and he discovered that there is a recharge of this aquifer, of this confined aquifer in the area close to the Ventania mountain range. Found in here, in this research area, waters that were dated by carbon-14, but as moving to the south, water was out of the carbon-14 method. Then that's why we decided to study this sedimentary basin, specifically to study the Miocene aquifers, in order to apply the methods of Krypton 91. We used several available wells. This is the total depth of the wells that we are studying, some of them more than 1,000 meters depth. And considering the well logs, we determine where's the position of the screens and the waters coming from which formation in every case. When we started the study, the first thing, or was one of the first things, was sampling for noble gases. The talking of the Professor Lu, and this talk is most focusing in krypton radionuclides, but initially we take samples for noble gases using these copper tubes in the field in order to analyze the total noble gas composition of the water samples. The samples were analyzed in the International Atomic Energy Agency water isotope laboratory. There are the copper tubes in the gas extraction process in order to analyze. And the information provided for noble gases is very interesting, because as they are non-reactive, the solution in water follows the Henry's law, and this solubility coefficient is related with the recharge, pressure, and salinity during recharge. Then the noble gases are giving us also information of the conditions when recharge. But moreover, it's interesting the study of these noble gases, because we in the lab they also measure the total amount of helium-4 present in the sample. And as it was said, part of the helium-4 present in the sample is not coming from the atmospheric dissolution, but these minerals contained in the sediments of the aquifer usually or always contain some parts of atoms of uranium and thorium which decay with alpha emission. Then adding more helium to the water, forming a new source of helium in the water. And then as much older is the water, as much time of water is in contact with the aquifer, higher is the amount of helium-4. Then the amount of helium-4 is also an indicator, a relative indicator the water age. In this project that when we are participating, this is the samples that we take in Argentina. This amount of helium-4 was observed that this is good indication that where Krypton-81 is an adequate method to be applied. It's not it's not a question as Professor Lu explained it. There are very few labs in the world for analyzing Krypton-81. It's very costly process, and then before sending a sample to the lab, you have to be sure that it's adequate to use this method. And a way to know this is measuring the total helium-4 accumulated in the sample, which is indicative that if you are maybe over 1 per minute ticks, more or less, which is about two times the two orders of magnitude the concentration in the atmosphere, your water is promising to be very old. And then you can move from this area that is used for carbon-14 analysis to this area where Krypton-81 is the available method. In this representation of our samples, and in this representation, this graph is a log scale here. There is a linear relationship from the ratio amount neon and helium. As neon is only of atmospheric origin or sources, as when the helium content is increased because of the uranium and thorium decay for the crustal component, your sample is moving from the atmospheric composition to the crustal composition. And possible to observe here, most of our samples are more close to the crustal composition, indicating that Krypton-81 can be an adequate method for sampling analysis. And well, then it's the part when we use the Krypton-81. The Krypton-81 is the product of this meeting in the CRP project of the International Atomic Energy Agency, as Professor Lu mentioned it. And before, after that, we find that there was a bilateral cooperation project between Argentina and China from the National Science Foundation of China and the CONICET of Argentina. And there wasn't also a way to start working together. Thanks to this, we received in May of the past year to Dr. Wei Yang of the USTC. And we were sampling for Krypton-81 in our basins in Argentina in cooperation with colleagues of the Universidad Nacional del Sur, Claudio Lexo, and also receiving the support from some conceptual aspect from the University of La Plata, Professor Eduardo Cruz. These pictures, you can see the complex amount of equipment that we need for a sampling campaign. This is the gas tractor machine, based on the hydrophobic membrane, as Professor Lu described, and this is the foil bags for gas samples. We have taken the samples in this kind of foil bags, special for bag samples, and different pictures showing the sampling campaign. That this tank is for cooling the water because it's thermal water in the area close to 60 Celsius degrees, and then water needs to be cooled before passing for the machine. Well, after sampling, the gas bags were prepared in a robust box and sent to the. What is saying this study until the moment? That's only very general schematic figure. But in this area, in the Colorado Basin, where the Professor Bonerino obtained measurements for Krypton-81, for carbon-14, again, we can determine some ages for carbon-14, but moving to the south, in the area where the ages cannot be determined for this method. It's possible to determine by using Krypton-81 ages as old as 900,000 years old. And this is very interesting situation in the Colorado Basin, because in the Colorado Basin, fresh water is obtained from the Miocene aquifer in this area close to the recharge. The water is hot, very hot. It's close to 60 degrees Celsius, but it's fresh water. It's drinking water, and it is artesian. People want to public faucet for water to use this water for drinking, because the water in the shallow aquifers, in the unconfined aquifer, is mostly the natural contamination with arsenic. And also some small towns have only a well for all the town, and it's supplied. The drinking water in the city is supplied by the thermal aquifer. But to the south, I'm sorry. Oh, I'm sorry. I'm very sorry. Here, I pressed the wrong. To the south, the water is used for a thermal resort. For tourism, is using to the south this very old groundwater, and then Krypton-81 is telling us about the very, very long time, the very low velocity in the movement to the south, and the probably contribution from the deeper Oligocene sandy aquifer, resulting in brines that more than 80 grams per liter of salt and water of very, very high temperature. That is, Krypton-81 is helping us to save for the understanding of this basin. And in the case of the basin of the Salado Basin, it's interesting because we are trying to discover if there is also, as in the Colorado Basin, and some research area, probably in the two borders. There is a research area. Our measurements for carbon-14 in the borders were in these amounts, as it was mentioned, but for Professor Lu, we have to consider that it's older than 30,000 years old water. We can get some measurement in one of the borders in this value, 640,000 years old. We were using Krypton-81, and to the center of the basin, the water ages are around 1 million. It's interesting, and in this area, the water resource is using also for thermal resort and spa. There is one thermal resort and spa in the area, but there is another, and there is another, and there is another, and there is another. There are by the moment 5 thermal resorts in the area, and it's interesting to answer to the question of how sustainable is the use for recreational purpose of this aquifer if the water is 1 million years old. It's clearly no renewability for the use, and it has to be considered the use of this water for thermal resort without regulations. Well, trying to go concluding, why Krypton-81 can be important for the region. As Professor Lu said, or it's easy to understand, Krypton-81 is important for hydrology. But in South America, we have a lot of deep aquifers that are poorly studied and poorly known. And this deep aquifer can be, in some areas, the only source for groundwater or for water for different uses for the population and the economic development. And they can also be used to complement polluted shallow aquifers. Also, the knowledge of the age, the water age, of the distribution of the ages of groundwater can be used for studying the management of mining water. Usually in mines, it's possible to have problems with leaking in fractures or flooding of the galleries in fractures, and it's important to use the Krypton 81 or other tracers to study the sources of these groups. As it was mentioned by Professor Lu in one of these examples, having water so old as 1 million years old or so on is a good indication that this area is isolated from the surface. It's very isolated from the surface, and that places can be used for nuclear waste repository in South America, Brazil, Argentina. I think that Colombia have nuclear reactors for energy, nuclear power plants. The management of the waste of the nuclear industry is still under development, and Krypton 81 can be useful to determine the degree of isolation of these areas. Also in South America, they are starting especially in Argentina, starting the use of fracking technology for oil and gas production. Fracking produces fractures in the formation, which is containing the gas and the oil, but these fractures can be also producing processes or fractures in the upper layers, and it is suspected that or said that can produce changes in the circulation of also superficial aquifers and promoting some kind of contamination of mixing of waters. And then also Krypton 81 can be, in my opinion, a useful tool for studying the behavior of water or the mixing of young groundwater and very old groundwater in areas where fracking is. Well, I think that's next is the last, and then how can we be prepared for the coming challenges? The challenge is to use Krypton 81. This is a fantastic tool. Noble gas radionuclides is a fantastic tool for studying hydrologic systems and everywhere in all the world. And in South America, we have to develop the capabilities in order to take the advantages of this one. We have to acquire an adequate know-how, fundamental of the method, the basis of the method, and how to use it. We need the international cooperation. In this picture, I think Professor Lu was preparing the AJA in the Argonne National Laboratory, and there are, until I know, maybe only 3 AJA laboratories in the world. And then it's necessary to work in international cooperation with the international laboratories, but not only because of the analysis, of course, but also for having the experience of the people who has developed the method and has a lot of experience in how to data interpretation, samples contamination, has to correct the sample contamination, etc. But of course, we also have to develop sampling capabilities to be able to take samples in the region. Until I know, in the region we have 2 available gas extractor machines. One that was developed in Brazil, which is one machine which is made in Brazil by the Professor Chang in Sao Paulo. And now we have in Argentina, our research group, this gas extractor machine that was donated by the University of Science and Technology to us for taking gas samples. Then having the equipment in the region is very, very important to be able to take samples before to send to the lab. And the last, it's more like a question, as the Professor Lu mentioned, is before to measure the sample in the AJA, is necessary to perform a krypton purification. It means that from the sample and following this series of traps to obtain only the krypton contents in a very, very small volume to send to the laboratories. If this process can be done in the region in South America. Many costs of shipping and handle samples of so on can be avoided, and also it can be very, very helpful for sure for the laboratories, because they receive the sample, can measure immediately without the necessary need to make this process. Then I think that is everything that I want to say. I want to try only to show the importance of groundwater for the region, and the importance to be considering the use of very old groundwater. Other applications of very old groundwater of study with Crypto91, not only for drinking water or for different uses, but the measuring the age of very old groundwater is very useful for understanding the water movement in deep sedimentary systems. Other applications, and these very special comments, because we have to be ready, to be prepared to use this technology, because it's, as Professor Lu mentioned, actually a very useful tool for studying hydrology. The picture when sampling with the Professor Dr. Wei Yang and my colleague Mauricio Quiroz. And well, thank you very much.
Okay, thank you. Congratulations for the presentation. We have a couple of questions. Thank you, Daniel. So Roberto from the Geological Survey of Brazil just want to say that he's just about to deliver some krypton helium ages for the Guarani Aquifer, and saying greetings for all colleagues. And he's also saying that's a very nice presentation, and make some questions. Did you manage to get NGT for both basins, and how did excess air components look like?
I don't have actually at this moment the data from the noble gases results. Yes, we have the noble gas result from both basins. The excess air component was, I think it's not very high excess, but well, I think that we can exchange some emails with Roberto, and I provide the precise values, but the excess was not very high in this.
Okay, and he's also asking, could you estimate percentage of the contribution of the underlying aquifer, Colorado Basin?
Oh, no. I think I'm not able at the moment to estimate the percentage of contribution. Probably, I want to say why. Because the wells, we have not wells taking water from the deeper aquifer. The wells, the valuable wells, only take the water from the Bucta formation, not from the other formation, from the Colorado formation. And this possibility of contribution of older groundwater is based in two things, especially. One is the very high salinity developed. This is very high salinity developed in the area. In only 60 kilometers, we passes from less than 1 gram per liter to 80 gram per liter, and also because of the very high gradient in the edge. But I think that we need more information, and maybe it can never be answered if we don't find a well that can take the other end member, the end member of the Colorado formation, in order to calculate the mix.
Okay. Also Sibeli Ezaki is saying congratulations on the presentation, and the application of noble gases and krypton-81 has brought a great contribution in the elaboration of hydrogeological conceptual model and other applications. For South America in particular, I believe it's allowing many advances in research. Adriana Cabrera is saying congratulations. The presentation is very clear and very interesting. Eduardo Cruz also saying congratulations. Margarita, congratulations. Thanks, Dr. Martinez. Greetings from Corrientes, Argentina. So if shall we have some questions from the other side?
Yes. So from our side, it's also many audience said congratulations, and this is a wonderful talk. And just one audience would like to ask is that the underground water can go to very, very deep. So how deepest the sample you can get it?
The deepest well that we sampled is 1,300 meters deep. In average, 1,300
meters.
Yes, 1,300 meters. Mostly they are about 800 meters, 900 meters, or 1,000 meters. The average deep.
Thank you very much. So so far there's no from my side, and so we thanks the Professor Martinez one more time. Sure. Thank you very much. So we will move to our next speakers. Let me share my screen. So the next speaker is also came from the University of Science and Technology of China. So Professor Dr. Florian Ritterbusch and Ritterbusch. So Florian is also, right now, he is associate scientist in the University of Science and Technology of China. Originally, he got his bachelor degree from Heidelberg University and also PhD from Heidelberg University 2013. So after that, he worked as the postdoctoral research at the Kirchhoff Institute for Physics, Heidelberg University, and also postdoctoral research institution for environment physics, also in the same university. Since 2016, he worked as the postdoctoral researchers at the University of Science and Technology of China. Since last year, he was an associate scientist at the University of Science and Technology of China. His research interests including the atom trap trace analysis of rare krypton and argon as topics for application in environmental systems such as dating of water and ice. So today he will talk how to get the age from the glacier ice and oceans. So Florian, can you hear me?
Yeah, I can hear you.
Okay, so it's your stage. I just stop my screen and please share.
And then this one. Yeah. And then this. Yeah. And then I have to press this. Right? Yes. Then you right click. Okay, hello everyone, and thank you very much for the introduction, and also thank you very much for inviting me to this forum. And I will follow up on the talk from Professor Liu on the dating of water and ice with noble gas radioisotopes. And as Professor Liu already described, dating with noble gas radioisotopes can be used to date the different compartments of the hydrological cycle. And in the past, due to the large sample size requirement that was needed for Krypton-81 and also argon-39 dating, so these isotopes were mainly applied to groundwater. But nevertheless, they are equally useful also for the other compartments of the hydrological cycle. So for Krypton-81, dating of glacier ice, in the past, more than 100 kilograms of ice were needed for Krypton-81 dating. And that amount of ice is, of course, impossible to get from a deep Antarctic ice core. So at that time, for the first demonstration study of Krypton-81 on glacier ice, the only way to get so much ice was to go to the margin sites where the old ice will resurface and where it can be sampled in big quantities. And because it is such big quantities, it had to be degassed in the field, in Antarctica, in this big tank here. Now, with our latest AJA setup at USTC, we could lower the sample size for Krypton-81 dating down to 5 to 10 kilograms of ice. And this brings dating of deep ice cores into reach. And also, the ice doesn't need to be degassed in the field anymore, but can be degassed back in the lab. So in practice, this looks like this. We take our equipment for ice degassing to wherever the ice is stored around the world. And then in that lab, we will put the ice sample into our tank. And then we will pump out the remaining ambient air from this tank. And once it's evacuated, we close off this tank with this valve here and start to melt the ice. And once the ice is melted, then the precious air from within the ice is released to the headspace on top of the meltwater. And from there, we can easily compress the air into the sample container. And then this sample container, rather than the ice, then it's this sample container that we ship back to our lab here at USTC for the krypton purification. And this krypton purification we do by titanium gathering in a hot oven up to 1000 degrees, followed by gas chromatography. And a nice feature of this new krypton purification system is that we don't only get not only get the purified krypton fraction, but we also get the purified argon fraction for argon-39 dating. And maybe here to answer on one of the comments of Professor Martínez, so one could think of not to the entire krypton purification to establish in South America or in other labs around the world, but we could think of to only implement this first step of the titanium gathering in labs around the world, which would already reduce the sample size quite a lot. So maybe we can discuss on that later further. And once the krypton fraction is purified, then we can use this purified krypton sample in our AJA system for the Krypton-81 measurement. Now these systems, they have been operational since late 2017. And since then, we have done several projects on Krypton-81 dating of glacier ice, mainly in Antarctica, but also on the Tibetan Plateau. So one of these projects at the Russian Vostok station is on one of the biggest puzzles in paleoclimatology recently, and this is the mid-Pleistocene transition. So we know from marine sediment records that the temperature on Earth has transitioned from a 40,000 year cyclicity to the current 100,000 year cyclicity. And this transition happened between 1.2 million years ago and 800,000 years ago. But what is the reason for this so-called mid-Pleistocene transition is pretty much unclear. There are theories that involve the CO2 levels in the atmosphere as the driver for this transition. To test these theories, a record for CO2 would be needed that covers this mid-Pleistocene transition. However, the only real archive for CO2 levels in the atmosphere that are ice cores, but the oldest ice core that has been retrieved so far, that only goes back to 800,000 years. That is why there's a race going on in Antarctica at the moment to find an ice core that goes back at least beyond 1.2 million years. However, it may also be that we already have such old ice, just that we were so far not be able to date this ice. One example for this is the Vostok ice core. So the Vostok ice core is about a bit more than 3,500 meters long and is very well dated down to 3,300 meters, where it reaches an age of 400,000 years. However, below the lowest 200 meters, the stratigraphy is disturbed so that the ice can't be dated anymore. Now, recently, our colleague Volodya Lipenkov, they developed a method to date these bottom 200 meters. This method is based on the hydrate growth in the ice. And they applied this method to this bottom 200 meters. And now if we plot that the chronology that they get for this bottom 200 meters, and if we plot it on the same scale as the original time scale, then we see that this chronology actually goes up to more than 1.2 million years, meaning that it actually covers the mid-Pleistocene transition. So this was a big surprise, and people get very excited, but this is a new method. So of course, you want to verify it with an independent, absolute, and reliable method. So this is why we got 3 samples from this bottom 200 meters of the core. Each sample was about 7 kilograms. And first of all, we measured the krypton 85 in these samples, and we see that it's below our detection limit. And this means that there has been no contamination with modern air during either sampling or sample preparation. And now if we plot the obtained krypton 81 ages on the chronology obtained with the hydrates, then we find that the krypton 81 ages confirm the original time scale. And this means that the Vostok ice core, if measuring CO2 level, CO2 in this ice core, it may already provide clues about what has triggered the mid-Pleistocene transition. Now, this was all about krypton 81, which is very good for old ice and old water. And now I want to shift to argon 39, which has a half-life of 270 years. So it covers the time range between 50 and 1,500 years. And as Professor Lu mentioned earlier, this isotope could only be measured by low-level decay counting in the past. And for decay counting, several tons of water were needed, which is why its use was practically limited to groundwater. Although it is also very useful for ocean circulations and also for alpine glaciers. Now, to realize an AJA system for argon 39 is very challenging because its isotopic abundance is 1,000 times smaller than for krypton 81. And this translates into an argon 39 count rate, which is 1,000 times smaller than for krypton 81. And due to that, a decade ago, the first machine that measured argon-39 only measured 1 atom in 5 hours. So 1 atom in 5 hours, that's of course far too low to measure environmental samples. But then in the following years, the argon-39 count rate could gradually be increased. And now our recent setup at USDC, we could reach 10 atoms per hour. And that actually allows us to now measure not only groundwater, but also ocean water and glacier ice. Now the first ocean study we did with argon-39, that was at the Yad Mariana Trench here in the West Pacific. And since our sample size is only 5 to 10 kilograms of water, so for these ocean studies, instead of degassing the water in the field, we actually sample the water in these Niskin bottles, and then we fill the water from these Niskin bottles into these pre-evacuated standard commercial gas bottles. And then instead of sending the gas home, we send this water home to our lab. And then in the lab, we do the degassing as well as the purification and the measurement. Now, just as a side note, so we were also thinking, and this is maybe also a point for discussion, whether this can be a solution maybe in the future for groundwater dating. Now coming back to the ocean, so since our purification system can not only purify krypton, but at the same time also purifies argon. So for these ocean samples, we could retrieve a krypton-85 profile. And if we plot the krypton-85 activity versus the depths in the ocean, we see a sharp decrease already in the upper few hundred meters. This is due to the short half-life of krypton-85, which is only 11 years. Whereas argon-39, which has a half-life of 270 years, much larger than the half-life of krypton-85, we see a much gentle decrease. And due to that these two different radioisotopes are sensitive for different time ranges, they are very useful to constrain what oceanographers call the time transit distribution, which is the equivalent to what hydrologists call the H distribution. And so this demonstration studies proved useful, and now there are many more studies undergoing to get more argon-39 profiles in the ocean, especially in the Pacific. Now for our first argon-39 study on glacier ice, we worked together with Professor Tian, and we retrieved ice core from the center of the Tibetan Plateau. And now you must know that to date ice cores from the Tibetan Plateau is notoriously difficult because the annual signal in the ice core is usually not preserved. And there have been examples for ice cores from the Tibetan Plateau, which there were the chronology and climatic implications derived from this chronology were published in Science or Nature. But later then it turned out that this chronology was actually wrong by an order of magnitude. So in order to avoid this kind of situation, we wanted to include argon-39 in this study to have an independent check. Now, as you can imagine, to retrieve an ice core from a high altitude location as in the Tibetan Plateau, where there are often harsh weather conditions, is a tough job and involves a lot of manual labor. But our collaborators, they succeeded and retrieved a 110-meter ice core. And then they constructed a chronology for this ice core based on layer counting. And on the top 20 meters, this layer counting was mainly done by measuring the signals from the bomb peak 1963 which is apparent in the tritium, the cesium-137, and also the beta activity. Then below 20 meter, down to 79 meters, the annual signal in the delta 18, in the deuterium, as well as in the dust, is reasonably well. So these markers can be used to count the annual layers. But below 79 meters, then this annual signal is kind of washing out, so they can't be used to count the annual layers anymore. But luckily, at the bottom, these annual layers, they become visible by naked eye due to the snowy, the bubbly white winter layers and the transparent summer layers. So that at the bottom, the annual layers can just be counted by naked eye. Now, if these three methods are combined, then the overall chronology for the total 110 meter ice core then looks like this, going up to 1,300 years at a depth of 110 meters. Now, these dating methods, these layer counting methods, they have the uncertainties and the ambiguities, and this is why we wanted to measure argon-39 as an independent check. And so we went there with our extraction device, and then we took several ice samples and extracted the air out of these ice samples into these sample holders. And then we shipped these sample holders back to our lab for argon-39 analysis. And then if we plot the obtained argon-39 ages onto this layer counting chronology, then we find that the argon-39 ages, they confirm the initial chronology fairly well, down to 70 meters. But then below 70 meters, there's a consistent deviation from the layer counting chronology. And if we look in a bit more detail, then at which depths, which layer counting method has been used, then it seems like the visual layer counting method has a problem. And this is why we are currently working on an optical line scanner system that can hopefully count the annual layers more precisely than we can do with our bare eye. Now, this has been, this is the first argon-39 measurements profile that have been obtained for an ice core. And this possibility, this argon-39 dating for ice cores now opens a lot of possibilities for ice coring in high mountain glaciers, such as the Tibetan Plateau or the Caucasian Mountains or the European Alps, and of course also the Andes in South America. And since this is a China, South America, and Caribbean forum, I looked a little bit into that. And there is, in fact, a lot of high-impact research, mainly led by the famous paleoclimatologist Lonnie Thompson, on ice cores from the Andes, mainly in Bolivia and Peru. And the climate records that can be, these ice cores provide, they're fascinating, surprisingly beautiful, and going back to more than 20,000 years. And I'm pretty sure that there are many more potential ice coring sites in the Andes for retrieving further climate records. And now going a bit further into the south, apparently also in the southern Patagonian ice fields, which feeds the famous Perito Moreno Glacier, there are sites for ice coring, but apparently so far no work has been done in these locations. So we are looking forward to maybe in the future to broaden the collaborations, not only in groundwater, but maybe also in these fields. And with that, I want to finish and thank for your attention. do something. Wait.
Thanks, many thanks for the talk. I was muted. And so is any question from your side, Diana?
Okay, no questions. Just congratulations. And it's very interesting, the presentation. Thank you. And I was wondering if in Brazil don't have ice, but we use some samples as standards in the lab. I'm wondering if I think it's important to have all this information about gases and in the ice in order to understand better the standards, but it's another issue maybe to relate with the Tirza presentation. So there's a question here from Roberto. If are there differences in NATO facilities between China and Heidelberg? And congratulations for the talk.
So the AJA system in Heidelberg is at the moment can only measure argon-39, and the needed sample size is a little bit higher, and the background is a little bit higher also for argon-39. But in principle, they can also measure argon-39, whereas krypton, currently there is no facility.
Okay, so there's no more questions.
Yes, so there's also a question from our side.
Okay,
there's the audience wondering, what do you expect the oldest ice? Is that will be from the top of the Everest or on the very ground?
Yeah.
So basically, where you expect it to get the oldest one?
Yeah, good question. So definitely not from the top of the Mount Everest. So surprisingly, all the ice coasts have been retrieved from the Himalaya. They're comparatively young. So they go back maybe a few thousand years or so. But because the glacier flows too fast. So in the Himalayas, because there's a lot of accumulation and there are steep gradients, so the glacier flows too fast. So there's no old ice. So the oldest ice will almost certainly be found in Antarctica. And today, the oldest ice that has been found there is 2.7 million years. But this is not an ice core. This is ice that kind of resurfaces from the bottom, and they just provide snapshots into the past, and not the continuous record that is provided by ice cores.
Thanks, Florian. So also there's the question from Emilio Martínez. Nice talk. In order to start preparing the sample at Perito Moreno Glacier, how are the characteristics of the Jury machine for ice core? Or is it possible to take samples from the glacier walls?
So it's also possible to, if you just want like a single sample and not an ice core, then it's also possible to sample at the outlet of the glacier, which would be the Perito Moreno. And there actually it's very simple to sample. It's usually done with a chainsaw. And we have done such work before on the Tibetan Plateau. And if you just are interested into single ages, then this is possible. Just go to the outcrop of the glacier.
Thanks. We also have one question from the audience on the screen, and he said the ice core should be mixed with some different parts of the ice, and how long it normally will take it for the samples to have the very reasonable measurement.
Okay, so I'm not sure I understand correctly, but if the question is whether it's about the length over which we sample the ice, that this will be kind of mixed.
Looks like how big is the sample for your ice core?
Yeah, so currently it's 5 to 10 kilograms. And we are in the process of lowering this to maybe 3 kilograms and maybe even lower in the further future. And yeah, if the problem is in fact that towards the bottom of the glacier, the annual layers, they are thinning rapidly. So then one layer can be only a millimeter or around. Then if you take 5 kilograms or so from that ice core, then in fact, you integrate over many years. And of course, this needs to be taken into account. And then this is not the age for 1 year, so this is the age for an integrated period of time. And also it can happen, and this is actually a big problem, that the layers within this range can mix. So the young layer, the old layers will be on top of the young layers of situations like this. And with Krypton 81 is kind of difficult to have a handle on that. So this is where really continuous methods for constructing chronology need to work together with the Krypton 81 to resolve such situations.
Many thanks for the talk. So since we're a little bit behind our schedule, should we move to the next speaker? So,
okay, okay, nice. Next speaker, I'm going to share my screen. Okay. So our next speaker is Miss Tirza Contreras Galeano. She is a civil engineer from the Central American Technological University of Honduras, UNITEC, and has a master's degree in hydrology and water resources management from the University of Costa Rica. Since 2011, she has been working at the National Electric Power Company of Honduras, specifically at the Francisco Morazan Hydroelectric Power Plant, where she has developed hydrogeological research applying isotopic hydrology to determine the origin of leaks in the dam site and its surroundings. She has participated with poster presentation in 2 isotope hydrology symposiums organized by the International Atomic Energy Agency in Vienna, and currently directs and coordinates as a country counterpart a regional project supported by the International Atomic Energy Agency, in which, in addition to isotopic hydrology, 2 more nuclear techniques are used. The project in question is called Strengthening of Surveillance Systems and Monitoring Programs. Monitoring for hydraulic facilities in the region using nuclear techniques to assess the impacts of sedimentation as a social and environmental risk. She's going to give us a talk about establishing the local meteoric water line in El Cajon reservoir, Honduras, using stable isotopes. Thank you, Tirza, and please.
Hello, everyone. Good morning for people in Latin America, and good night for you guys in China. So I'm going to share with you our experience that it's pretty much different it's not about Krypton 81 and those things. I would like to share with you our experience in Honduras. As Veridiana say, establishing the local meteoric water line in El Cajon Reservoir in Honduras. To put you in context, I would like to say that Francisco Morazán hydroelectric power plant is actually, it's commonly known as El Cajon in America and in Honduras, right? And it's actually the most important energy project in our country. It has a capacity, an installed capacity of 300 megawatts of production. It's located on the central part, almost in the central part of our country. It's located between three departments. It's located between three departments, and it is almost close to two of the most important cities of the country, Tegucigalpa, which is the capital, and San Pedro Sula, which is the industrial zone of the country. The basin area of the, it's about 8,220 square kilometers. The reservoir area has an area of 94 square kilometers. It has an average elevation of 930 meters above sea level, and we have an average rainfall of 1,000 to 1,500 millimeters annual rainfall. So why did we decide to establish our local meteoric water line in the reservoir area? Since in 2003, the Civil Engineering Department of the hydropower plant developed a project with the support of the International Agency of Atomic Energy called filtrations in El Cajon Reservoir, because we have some important leakage in the right side of the dam. So this project promotes the use of isotopic and hydrochemical techniques to understand where this leakage was coming from, if it was from the precipitation or it was only from the reservoir. So this project covered not only samples from these filtrations, but also taking account samples from piezometers and hydrometers that are located inside the dam. So the results were very spread. They can see that the water from the filtrations of this right side of the dam belongs to water from the reservoir, but they have some data inside the dam that they were wondering where this leakage come from. So to have a better understanding of the hydrological behavior of the area, and in order to correlate the data from springs that are located downstream the dam, leakage and other filtrations inside the dam, is that in 2012, we have decided to start the construction of our local meteoric water line. And how did we do this? We installed 7 rainfall collecting stations all over the reservoir, as you can see here. These are the 7 stations. And we consider, to install them, we consider some important things as the easy of access, and if we have some people who can take care of these stations. And of course, we take in account the difference in elevation, as you can see over here. So we can correlate this data with altitudinal effects and these things. So we have data taken in continuous way from the year 2012 through May 2015. But we have data from precipitation only from the years 2012, 13, and 14. So in order to correlate this data, the data that we get from stable isotopes, oxygen-18 and deuterium, I will only show you data from 2012 through April 2014. This is just an example of how we got some data that we have in 2013. And we have some results of this data. We can see a stational variation of the oxygen-18 data, which show us a bimodal behavior of the oxygen-18 and from the deuterium. I forgot to tell you that we have, as you can see in this monthly precipitation data, or rainy season, it's from May through October, more or less. And then from November to March, we have a wet season in our study area. So as you can see, we have more negative data in the wet season, and less negative data in the dry season. The same happens with data from the deuterium in the study area. And we have this DXS data. As we know, it is important to have this correlation to know about the evaporation processes in our study area. And as you can see, we have three stations which shows a little bit different behavior from the other ones. And these stations correspond with the ones that are located over here. It's this one, and this one. So probably this is showing us that we have the region of the rainfall in these stations. It's from a different mass or something like that. We also have seen that the quantity effect of it's pretty much dominant control in the temporal variation in this study area, as we got the data show us that as more quantity of precipitation, we got more negative values of oxygen-18. And we haven't seen an important altitudinal variation in our data. It only presents rates of change in order of 0.02 units of fractioning of oxygen 18 and deuterium per 100 meters of altitude. And using all this data, the data from these years, and using the ordinary least square regression, the local meteoric water line could be defined in your study area as this equation over here. We can see it over here. We have the global meteoric water line, and we have our local meteoric water line, which is this one in a black over here. And nowadays, this data, we have started again to collect data from the rainfall in 2018, and in order to get more data about or precipitation isotope composition in their study area. But nowadays, this data have helped us to make more correlations with data inside the dam. As we can see over here, this is our local meteoric water line and our local meteoric water line and a global water line. And we have, as you can see, all over the dam, we have different results of water. So we can now have a better correlation of this data using our local meteoric water line. So in a pretty much resume, this is what I want to share with you, to show you what we have been doing in our power plant. Thank you very much for your attention.
Thank you, Tirza. Thank you very much. Nice talk. Can I ask you a question?
Yes.
Where do you did the analysis?
Oh, I'm sorry. Yes, we didn't. We have. I didn't talk about that here. We have a chemical laboratory in Honduras, in our company.
Okay.
And we have this Los Gatos laser equipment in their laboratory. It's located here in Honduras.
Okay.
In the capital, Tegucigalpa, yes.
Okay. Okay, thank you. And another question, do you use this data to monitor the dam for preventing some problem or disaster, anything of that, or just
basically to know the origin of leakage, on 2015, and that's why we stopped taking samples. We have this important project that consists in reduce some important leakage in the dam. So this data help us to know the region of this dam and where to work in what direction should we work to stop this leakage in the dam.
Okay, so this data are frequently produced by you just to maintain the security of the dam.
The security of the dam, yes, and to know, for example, actually we have an important spring that it's getting lower and lower water in there. Okay. So we have used this data to know what is happening with that, if it's up to the descending on precipitation, of it's that some connection with the reservoir or things like that.
Okay, so we have another question here from Didier Gastman. Do you relate the variation on isotopic values of the reservoir water due to evaporation?
We do have some samples of the reservoir that we actually this data has been taken with this project that it's taking in account two other isotope techniques. And yes, we have seen the evaporation in the reservoir, but we don't have enough data right now. So we are still taking samples, and yes, we will correlate it with this data. This data with data from the reservoir. We are taking data from the reservoir at 3 levels in height.
Okay. Okay, thank you. Shabo, do we have some questions from Billy? You are not, your microphone is off.
Yes, yes. My microphone was muted by. Okay, so so far there's no more questions, but only congratulations. So very nice talk. And since we are a little bit behind our schedule, I think we will skip our previously the roundtable time, and we thanks all the speakers, and this is a very wonderful night, and I think this young scientist future will become very nice platform to get together all the scientists from China, the Latin American, and also all of the world. And for the next topic, or for the next thematic, we will focus on our life science and also for our different high technology. So please join us for the next meeting, next workshop, and we will make an announcement before. And this is very nice starters, and many thanks for Professor Lu, Professor Martinez, Professor Yingli, Shi, Franco, and all of the organizers and support.
Okay, it seems that Shabo has a problem with the internet, but I just want to make a closure in this talk. We had lectures just from the beginning of the instrumentation of new techniques, from paleoclimatic for global warming issues to sustainability and disaster prevention also. So we have isotopes. This is an issue, an important issue. It's considered the most incredible development from the last years in the geochemistry science. So it's important to share this with all the world, and also to improve the analytical methods and improve the techniques. We also have problems of internal standards of the labs. We have to share common internal standards in order to produce data with efficient comparison between each other. And that's, I think that's another challenge for us also. the International Atomic Energy Agency started a group of Latin America group for isotopes analysis in laser spectrometers, and just for create internal standards common to these groups. We have today standard from EIA is just not enough to get the whole scenario of isotope signatures we have in groundwater for hydrogen and oxygen. It goes only until 0. So we have melting from glaciers that has more negative, and we also have samples that are positive in Brazil. In all rain samples from South America, we have this issue. So we have to create a group, and we have to stay together in this kind of challenge with the internal standards and labs. And sometimes we have all the equipments. We have some equipments at the university, but we don't have the technique to analyze that kind of sample. So this is important for us to share and make partnerships in this researchers. And for finishing, and the most important thing for me is to strengthen the science and the cooperation and the science method in the political scenario of the world today. Because in some countries, especially I think in Brazil, we are facing this, the people that don't believe in science anymore. So we have to stay together. And I think to strengthen the science, it's up to us, okay? So thank you very much for all this. I'm very glad to be a part of it. And I thank you very much. I will pass the the word for other person. Thank you. If anyone wants to say something, please.
I was unmuting my phone, my microphone. Thank you everyone. Thank you, Professor Lu. Thank you, Veridiana, Martinez, Tirza, any of you. Thank you very much. I think it was a wonderful session. Many people watching. We learn a lot from you, and we expect to. We are preparing the next workshop, so we will give you and provide information through all our channels. See you soon. Bye-bye.